start recording. Okay, so this is the second example. Start from this grid, and there's a component called quadrangular division, divide. Okay, abbreviated as quad divide. So we have an input, it's a surface, and then for the U direction and V direction, we can set up the number of divisions. Okay, and then this breadth for, okay, this one somehow is not so clear. Okay, later we can see when you have different input for this, then what does it make a difference? It is strange because here it's a breadth, but if you take a look at the icon, you see this icon with a 7 inside, a hexagon with a 7 inside, it indicates that it is a number. But somehow this input parameter is called breadth. I'm not sure if this is a mistake or it is intended, but somehow it is strange. Okay, and because I don't find any where to explain this, so we just leave it alone. So this is very useful because then you can have quadrangular dissection for this breadth. Of course, you find also some other component, like I think like in the lunchbox or Grasshopper itself, you have some way to do something like this. Okay, but there are some cases which make this, maybe when you look at it, you think this is very simple, but there are some cases this can be a difficult task to do. First, you see this is a breadth. So I am not sure because here, yeah, this is a breadth. It calls surface, but you see this icon here with a cylinder, right? This hexagonal icon, which means it takes the input as breadth. Breadth is kind of party surfaces. Okay, so if you use lunchbox or use Grasshopper component, you can have this quadrangular dissection or quadrangular grid for surfaces, but you are not able to do it for breadth. Okay, so then this is very important because in some cases we do have party surfaces and we want to divide it with this kind of rectangular grid. Okay, and we can modify the number of divisions. Okay, and somehow if you change this parameter, the shape is slightly changed. Okay, but I can't really figure out what does it mean. So we just keep it 0, then you always get the same shape. Okay, and you see what you get is a mesh. Okay, in this case, I think it is the same as regular Grasshopper mesh, but in some other way of division, you get NGon mesh. Okay, another example, a breadth. And what does it mean by Chebyshev? Okay, so it is still rectangular, but this one is slightly different. First, it tries to keep these rectangles planar. I think it is not necessarily planar, okay? But I think, okay. And you can specify some point so that the grid will match this point, and you can specify the required length. And it is small. How come? It takes, what happened? Takes a while to do the computation. Okay. Okay, it doesn't like me to make it too small because it takes a while. I think it is trying to planetize this these rectangles. Okay. So you can set the length for this division, and you can rotate it. Okay, you can rotate it. Okay, this is controlling the number of iterations in the process for optimization. Okay, because this computation cannot be done analytically, so it has to run through a set of iterations. And here with this no, not R. These steps you can set up. You can decide how much time you are willing to offer for this operation. And I think, it's the maximum number of steps to walk from the starting point. Okay, I think it is a parameter which consider how much time concerning how much computational time. And this one you can have a switch to turn it on and off for extension. Okay. When it is false, it's like this. When it is true, the same. No change. I think it should be somehow try to extend toward the boundary. Okay. But this one takes more time for computation. And this one, prep, now we have this shape. And we want to have a diamond division. Okay, so each of this shape is divided in a diamond shape. This is not the same as rectangular grid. Okay, of course, if you rotate your viewpoint, then you can think of this as kind of a rectangular grid. But this is concerning the UV direction. So the division of this diamond, this pattern, following the diagonals of the UV direction. Okay. Of course, you can still have two parameters to control the divisions, but the orientation of this diamond shape is parallel to the diagonal of this UV line. And again, you have this boundary. If we turn the boundary on and off, then you can see it is different. See, we want to keep the boundary in two different ways. To flip it in or flip it outward and swap swapped UV direction, I think. No difference? Okay, now why is that? Here, when I turn the boundary to be true, to be false, then here we have a line that divide this set of diamonds into triangles. Okay, and why there is a line? This is the theme of this surface, because this surface actually, if you unwrap it, this is one edge of the surface, and this one is also the other edge of this surface. Somehow this is a seam that merge the two-sided of the surface into one. Okay, and when you try to divide the entire surface into a continuous pattern, then you somehow you cannot avoid this problem. Let me see if I use the even number. Yeah, if you have even number division, then at least visually you can overcome. So you don't see this thing. Okay. Okay, but when you turn on this boundary part, then it uses another strategy to treat the boundary of the surface, and somehow it's become you derive these holes. But when you can turn it off, then it is okay. But if we take a look at the true division of the mesh using clear, this clear component, then you see actually each of this diamond shape consists of two triangles. Okay, but somehow in the NGon definition, these two triangles are merged into one diamond shape. Okay, so instead of using one quadrangle to represent each of these diamond, it uses two triangles. Okay, in this pattern. Flip the sided of the mesh, I guess. Okay. Okay, now hexagonal division. Okay, they are all hexagons, right? So we can change the U and V. Okay, and this T is a parameter for hexagon. When it is smaller than 0.5, then it's kind of regular hexagon. But when it's approaching 0.5, they become rectangle, right? But you see, this is exactly this zigzag pattern arrangement. So topologically, they are hexagons. So you can change this by changing this parameter. So how about if you go more than 0.5? Two sides of this hexagon become indented. So it becomes this kind of shape. Okay, so topologically, this is also a hexagon because it is a six-sided polygon. And the boundary, okay, you can choose one of the three ways for dealing with the boundary situation. Okay, and for this hexagonal pattern, you can have three different ways based on the UV direction. 0 means you have this kind of smooth boundary for both U and V direction. But if it is 1, then you have both sides having this kind of zigzag pattern when it is on the boundary part. Or 2, now one side is smooth, the other side is zigzag. But if you want to switch, then you can swap them. I think it's this one. Swap. Okay, so you swap U and V using this one. Okay, and then quadrangulate. Okay, you don't find anything wrong, but the subdivision of this hexagon. So if you quadrangulate it, then you divide each of these hexagon into two quadrangles. So you can turn it on and off. Okay. Okay, you want to orient breadth faces and subdivide according to average breadth edge length. So now we think about this very simple breadth. Consists of, they are 1, 2, 3, 4. They are quadrangles. Okay, because here the angle the corner here is truncated, so it becomes a quadrangle, and it consists of 8 quadrangles. Okay, 8 surfaces. We join them, so now it becomes one single bread. And then we have to sort. You don't see any difference. Okay, and then you can divide it into quadrangles. Okay, now you see that these quadrangles follow the original bread structure. Okay, the original bread structure divides this shape into triangles. So now you do this quadrangular dissection, you can see that they are following the boundary, and you can change the dimension of it, and also dimension here. Oh no, you cannot change the dimension for V, so it doesn't make any difference here. Rebuild, this has something to do with the regeneration of the mesh, but here I don't see any difference. Maybe for this shape it doesn't do anything. Okay, so this is without sort bread, but how about if we sort the bread? I think for this example it doesn't change anything. Okay, so you basically find the same. But there is another example. Then you can figure out why sometimes we need to sort the bread. Okay, the sort the bread, actually it means that we have 8 surfaces, right? But when we use join, actually we imply that, or we assume that there is some certain order and some certain orientation to join this bread. Okay, and sort bread, internally this is a component from NGon. It will try to reorganize this set of surfaces. They look exactly the same, but the internal sequence and orientation are sorted based on average breadth edge length. Okay, so that when you do this further subdivision, then you can somehow make it better organized. In this case, it doesn't make any difference, but in other cases, it does make some differences. Okay, for example, like this one. Now we have surfaces with different shape and different sizes, different dimensions. There are 10 surfaces. You join them, and then you sort it, and then you apply this hexagonal division. Then you get something like this. Okay, again, because hexagon, so we can change the parameter. So you can get indented hexagon or convex hexagon. Okay, this is concave hexagon, convex hexagon, or rectangles if you have 0.5 for the parameters. And there are some singularity, for example, like here. Why is like that? Because they are the intersections of these breadth surfaces. So these are the singularities of this configuration. So when you try to divide this into hexagonal areas, there are some patch. You can never make them as hexagons. So for example, like this one. And they are the intersecting points for many surfaces. So let's think if we don't sort it. You see? Now there are problems for this subdivision. Okay. Somehow they need to reorganize the surfaces. Then the algorithm for dividing this surface into hexagonal patterns works. So you need to use this component to sort the bread, and then you divide it. Then it will work. Okay. So you have switches for. Okay, I think we have already talked about this. Okay. merge seams. We have a number of breadths. Every time, for every example, we simply choose from one of it. So we start from the number 0, 1, so which is this one. Okay, consists of a list of surfaces, and altogether there's a hole in it. And we can divide them as hexagons. Actually, in this case, I don't know other plugin, for example, like Lunchbox. I think Lunchbox you cannot do this. Okay, an area with holes in it, but with this NGon you can do something like that. And here is simply a way to calculate the sizes for division. Okay, we just ignore this part. Okay. And then again, you have these parameters to switch from concave to concave hexagons. Okay, and remember this one clear? If you use this clear, then you see that each of these hexagon is further divided into 1, 2, 3, 4, 5, 6, 6 triangles. Okay. Oh, we have checked only the first example. Now we can check the second example. This torus, we can apply hexagonal division to this torus. You see, when you look from the side, you see this indented part, because it is trying to use hexagons, okay, to approximate the curved surfaces. These hexagons are not planar. When you take a look at the vertices very carefully, they are not planar, because each of these hexagons consists of how many? 6 triangles. Okay, each triangle is of course planar, but 6 triangles together, they are not planar. Okay, and somehow this algorithm trying to use these non-planar hexagons to approximate the entire surface, because the surface is not developable. Okay, so they cannot be converted into a planar shape, but somehow this algorithm trying to approximate it. And later we can see that there is a component trying to planarize all these non-planar polygons. Okay, it may or may not successful, depends on the basic configuration. Okay, but anyway, this way. So if you show the subdivisions, then you see that each of these hexagons consists of 1, 2, 3, 4, 5, 6 triangles. And let's take a look at another example. This one is a cylinder. So if you look at the side, you see this indentation of the boundary. It's because it tries to use this kind of a concave hexagon. So if we change this parameter to be smaller, yeah, still indented. But yeah, even if we use 0.5 exactly, it is still indented, because these rectangles are zigzagged. Okay, if they are aligned, then you don't see this, but they are zigzagged, so you cannot have the same, you cannot align the boundary of it. Okay, quick, go on. This one, okay, for this shape, again, okay. So it just shows you many different situations. Okay. Platonic objects. Don't see it? This is a geodesic dome. Okay. If you take a look at this component, this is also from NGon. Okay. The first parameter, you have 4 choices. If it is 0, then it gives you an icosahedron. If it is 1, then it gives you a torus. This is strange because a torus is not a Platonic polyhedron. Okay, torus is not Platonic polyhedron, but I don't know, somehow they decide to have this option, which is to create a torus. And when it is 2, then you get a cube, yeah, which is of course a Platonic object. And when it is 3, then it's a tetrahedron. Of course, it is also a Platonic shape. But there are still some others, for example, like dodecahedron, you don't see it here. And octahedron, you also don't see it here. So I don't really understand why they call this component as Platonic. But anyway, there's an interesting thing. This is the radius, the size of it, of course. And you can have, you can define a plane so that this Platonic shape will align to this plane. And here you can decide the subdivision level. So this is a true level subdivision of an icosahedron. And this is a typical geodesic dome. Actually, I should say geodesic sphere. Okay, this is without any level of subdivision. So it shows you an icosahedron, which is an object consists of 20 right triangles. Okay, how about if we have first level subdivision, then each of the triangle is divided into 4 subtriangles, and then the vertices are projected onto the sphere that encloses this icosahedron. So this is the first level. With the second level, then each triangle is divided into 1, 2, 3, 4, 5, 6, into 9 triangles. Instead of 4 in the first level, in the second level, it is divided into 9 triangles. And in the third level, each rectangle will be divided into 16 triangles. So now it will consist of 1,280 triangles for the entire sphere. Okay, and now this is very interesting component, which is also very useful for architecture designers, which is the dual of the mesh. You see, they become hexagons. Okay, now I see why this Platonic component give us only 3 of the 5 Platonic objects. There are 5 regular Platonic objects, right? Tetrahedra, cube, octahedra, dodecahedra, and icosahedra. Okay, but cube and octahedra, they are duals of each other. Okay, so if you want to have an octahedra, then you create a cube and then you find the dual of it. Then you get octahedra. Okay, and here when it is subdivided into, okay, let's go back to the 0 level. Okay, these are all triangles. Okay, but if we find the dual of it, then you get dodecahedra. Why? For each of the triangle, you connect the center of the triangle. So here you see 5 triangles share the same vertex, and then if you connect the center of these 5 triangles, then you get a pentagon. Okay, then you get this dodecahedron. So you don't need to create dodecahedron from this Platonic component. Instead of doing that, you create an icosahedron, and then you find the dual of it. Okay, and you can do the same thing even with more subdivision levels. Okay, so now you have triangular dissection, but if you find the dual of it, then you get hexagonal subdivisions. So as an architect, if you want to design a sphere, then probably some of this construction is a good solution for you. Okay, so if you use the dual of this subdivision of icosahedron, then you're able to build a sphere-like construction using only pentagons and hexagons. Okay, if you prefer triangles, then you use this. Okay, if you want to use hexagons and pentagons, then you use this. So no matter how many levels you have, eventually you get 12 pentagons, and all the rest, they are all hexagons. Okay, so as architects, we need to know this. It's very, very important. And we can go on. We can cut this sphere based on some plane. Okay, here we just simply define some planes, and then we can cut it. Okay, and this component will cut it for us. So it is very useful operation for architecture designers. Okay, and the result, you have a mesh and then you cut it, and then they give you a set of polylines. But in NGons, polyline, enclosed polyline and mesh, they are convertible. Then you can use this from polyline to convert them into a mesh. Okay. And for example, this one, we have this dual. Okay, and now we can try to find planar. Okay, planar, you see the explantation? Planar ties neighbor faces NGons. So you don't see it, but I think we can preview it. Okay, now you see it. It looks similar, but somehow it tries to planarize these polylines. Okay, and you find the boundary surface of it. Okay, if you understand how this component works, you will know that if you have non-planar polylines, you won't get any output using this component. This is a regular, I mean, this is from the Grasshopper surface. Which is this one. Okay, so for example, if we use this before it is planetized, let me see. Let me convert this into NGon. Where is NGon? Get the polyline. Okay, so this is the mesh, and we derive the polyline. And before, if we don't do any planetization, then we try to get the boundary of it. You see, you get only pentagons, because when you do this subdivision of this Platonic object from icosahedron, no matter how many times you do this, how many levels of subdivisions, you always get 12 pentagons, right? And you need to know that only these 12 pentagons remain planar after you do this subdivision. Okay, all hexagons are no longer planar. And this is very important for architectural designers. Okay? And somehow they have an algorithm to try to fix this. So if you apply this component, then somehow you still get planar hexagons. Okay, and I think this is remarkable. Okay, this is remarkable. Very important for architectural designers. Okay, you understand this? Okay. Okay, and you can cut it. Okay, and I think you can still planarize it. If we try to find the boundary, you see only pentagons are here. But if we try to planarize it, let me see. And then we check. You see, they appear. Okay, so these are planar surfaces, and this is very, very useful. So after you have planetized all this one, then you can use a CNC machine to cut plywood to make these panels, and then to join them, and then to make this curved surface. So this is very important for digital fabrication. So that's why I think this plugin is very, very useful for us. Okay, let's start here.